Okay, so without further delay, I'll pass the mic to Roozbeh to continue his course.
All right, thank you very much. So just to remind you what we have done. So I'm gonna basically follow. So you can find this in archive. It's called Leavitt algebra versus Leavitt path algebras. And if you recall, so it's on archive. So the question was, well, you have all kind of graphs, but you have also these very particular graphs, which gives you the original Leavitt algebra. So this gives you Leavitt algebras. And then you have all kind of graphs. So can you give me a criteria that if I hand you a graph and you get the Leavitt path algebra, you tell me that you are not constructing any new example. It's already one of these. How can you say that? Right? So when you get a graph, you get a new example apart from these. And well, let me just put this as a conjecture. The conjecture said that if you have LE and if all finitely generated projective modules are free projective modules over LE are free, i.e. of this form, some copies, then LE has to be really L of some loops like this. And we had a lemma, so let me just write the lemma here, that this is equivalent to saying that if you have ME, remember ME? So this is just free module generated by vertices. And then if you had this relation here, then U is the sum of adjacent vertices. So these are the relations. And then this conjecture would be translated to saying that for any vertex you get, any single vertex you get in ME, you would be able to write it as some copies of 1E. So 1E is just the sum of all the vertices. You collect all the vertices. And if all finitely generated projective modules are free, means any V is of this form, and if and only if any V is of this form, then you can say that finitely generated projective modules are free. So in a way, it's really a simple game because you only have one, as far as I know, you only have one tool, and the tool was the confluence lemma. So the only tool I know is confluence lemma, which told you that if two things are the same, so you go back and forth and you just use this from one bunch of vertices to another, you use this. If they are the same, then it has to move in one direction and give you Z. That's honestly, that's the only thing I'm gonna keep using, back and forth, but with different flavor to get results. So in a way, again, as I said, it's really an undergrad project. So imagine you have this equality. This is the only tool you have. What can you say about the graph? Can you describe the graph? The graph which has this kind of property. Okay. And then one test was here, if this conjecture was supposed to be true, one test was, let's look at the Mn of R and look at this projective module. We know this is a projective module because I can complete this with the 0 here, and then R I put everywhere here. And I recover Mn of R. So this is a projective module. And it's finitely generated projective modules. But if this is supposed to be free, that means this would be copies of Mn of R. It's kind of intuitively weird because Mn of R everywhere is filled with elements of R. And you just put them next to each other and you add them. How come you just get them all 0 here, right? So it's intuitively, it's not possible. So let's try that. Let's try this conjecture in this setting. Okay. See what happens. So I'm going to get the usual Leavitt algebra Ln, which is just n loops, okay? And I put it into a matrix. Let me get the indices right. Md of Ln. So I'm going to look at this, and this is a Leavitt path algebra. This is a Leavitt path algebra. It's the Leavitt path algebra of this. So you have n loops here, and d minus 1 edges going from u. Let me just get the from u to v. So this is u, this is v, and these are just the loops. So this graph with n loops and d minus 1 edges would give you matrices over Ln. Now, suppose all the finitely generated projective modules here is free. Okay, so imagine conjecture. So SC, consider SC. Serre's conjecture. All finitely generated projective modules are free. Okay. So in particular, it tells you that, remember that lemma, that any V, any vertex I get here is k copies of 1e. Okay, so now it's a bit of computation. I'm going to go through this. Hopefully I don't get stuck. Okay, but what is 1e? But 1e is just sum of the vertices, 1u plus v. Okay, so I'm in this situation that v has to be some copies of u plus v. Okay. Okay, now k. So what is u? Can you tell me what is u in ME? Because I'm working in ME. What is u? U is the sum. Please help me here. So u has to be the sum of all these vertices. So I have v, this is my v, plus, what is u, you think? So you have to go along all the edges and get these vertices and add them together. So there are d minus 1 of these going out. So I get d minus 1 v. So I get d, yeah? Yeah, I think maybe I didn't write it. So this is u, this is v, and then there are loops here. It's all in one vertex. And these are all also coming from this vertex to this vertex. So there are only 2 vertices here. There are only 2 vertices. Okay, so instead of u goes to d minus 1 copies of v. So I just put it here. So do a little bit. So I get here k dv. So far, in this monoid, ME, v is k dv. Now, the only tool I have is the congruence. Namely, if v and k dv are the same, I know that they go to the same thing. Okay, so let's do a bit of calculation here. So you have V. If it moves along this one here, what do I get? So V is here, and there are n loops. So V has to be the same as NV. So if V moves, I get NV here, right? And then again, if I want to move this, so you have NV, so that's V plus n minus 1 of V. You get one of them, and then you do this again. You get NV plus n minus 1 of V. And you keep doing this, right? Same story here. So you have KdV, but each time you get one of these V's, and you just replace it with NV. And you do that. So if you do this calculation, you see that what I get, if each time I move it, I get one n minus 1 of V more. Then again, I get n minus 1 of V more. So if you do this, I times here, I get to V plus I n minus 1 of V. Same story here, but you have KdV as a coefficient. So you get V, maybe this time you do J times. Who knows how many times you do this to get here. So plus J minus 1, J times n minus 1 V. Okay, I'm here. So let me just do a little bit of cleaning. So here I get 1 plus I n minus 1 of V. And here I get KD plus KDJ n minus 1 of V. But then remember, now I'm in, when I get here, this is when I get here. This is in the free monoid. This is what also really mentioned that to me. So this is in the free monoid. So in the free monoid, if two things are the same, V's here, they have to be the same thing because it's a free monoid, right? The looks should be the same. So then these two are the same. So then I get 1 plus I n minus 1 is the same as KD plus KDJ n minus 1. Okay. So what do I get from here? So if something divides n minus 1, and at the same time it divides d, what happens? If something divides n minus 1 at the same time divides d, so it's going to divide this, it's going to divide this, it's going to divide this, then it has to divide 1. So then the greatest common divisor of d n minus 1 is 1. So I got here. So where did I start to get here? I assumed that in this Leavitt path algebra, all finitely generated projective modules are free. That's the assumption. And I got here. And then if you look at the books in Leavitt path algebras, you get this very interesting theorem already established, that if GCD of d n minus 1 is 1, then miraculously, this is isomorphic to this Ln. So the conjecture is correct here. Although in your head, it's just very strange that one copy of R should cover the whole thing, but it happened. So as a test, this conjecture is correct here. Now, a couple of theorems. So we don't know if this conjecture is correct or not correct. Either way is good. If you get it's not correct, then question number 1 fails. If you get it's correct, then question number 3 is correct, right? So either way, yes or no, you always get a good answer or good consequences. So here is the first theorem in here. And again, the only tool we have is the confluence lemma. So in order to get results, you have to just be patient and work with this confluence lemma. That's all. So theorem is a finite graph. And suppose Serre's conjecture is valid, is true, i.e., all projective modules are free. Suppose that. Then Leavitt path algebra should be either K, which this means that it's just one, the E is just 1 point. If E is 1 point, then your Leavitt path algebra is just one copy of your coefficient ring. Or your Leavitt path algebra is a Laurent polynomial rings. You have seen this now. And this means that E has to be just this. Or finally, your Leavitt path algebra is purely infinite simple. And don't worry about this. Just imagine that means that the graph E, everything is connected to everything. So all the any U and V you give me, I can connect it in both ways, strongly connected. Everything is connected to everything. So already interesting, right? So I put the assumption that finitely generated projective modules are free, and I get that everything is connected to everything. And not only that, and so you have seen the K0, the formula also for K0, which comes from this adjacency matrix. This is of the form of Z and Z. And this special element goes to 1. And this is the language I'm using. So the K groups is just a billion and torsion of billion group of this form. And this special element goes to 1. So it gets this form. And I want to show you a little bit of a proof just to see that I don't have that many tools, just confluence, i.e. if you concentrate, maybe you get more than I'm just doing here. Okay. So proof. First of all, if E is of this form, or is of this form, of course, the Leavitt path algebra, I know for a fact that the Leavitt path algebra is K or the Laurent series, okay? So if E is this or this, then, well, then the Serre's conjecture is correct. Because we know, we mentioned that for field, any module is free. For PID, any finite generated projective module is free. For these are okay. If E is this one, so one vertex and n loops, well, of course, first of all, the conjecture is true, and this is a purely infinite simple. This is what we wanted, that everything looks like this, and of this form. So for a graph of this type, we have it, it falls into these three things, so I'm okay. So now suppose your graph E has more than one vertex. So now I have to give you a remark. You know, it is possible I give you a graph which has more than one vertex, but the Leavitt path algebra is isomorphic to loops. This is possible. So that brings complexity. So look, I can give you this graph, and you can, well, it has two vertices, and this doesn't look like loops, many loops. But the Leavitt path algebra of this is isomorphic to this. So again, it is possible your graph doesn't look like 2 loops, 3 loops, but the Leavitt path algebra is isomorphic. So that brings complexity. Okay. Now, suppose your graph has more than one vertex. First of all, what does that mean? That means when I write 1e, 1e is the sum of the vertices, right? So 1e has more than one, how do you write it? One component, one sum. So 1e is the sum of the vertices. So therefore, 1e, when I'm writing, has more than one, what, sum, entry. Say it again. Yeah, how should I write it? So has more than, okay, more than one letter. If you understand what I mean, that because E has more than one vertex, so it has to have more than one thing appearing here. Okay, so keep this in mind. Okay. Now, suppose I look at ME. ME is the graph monoid associated to E. Well, now I want to look at the structure of this. And suppose you have an ideal, an ordered ideal inside. This is an ordered ideal. Okay, so now let's see what happens with this I. So because I is not 0, then there is an X, there is a non-zero element inside I. But what is this X? How does X looks like? Well, X comes from ME. And ME is just sum of the vertices, some bunch of vertices. So X is a sum of vertices. It could be with multiplicity. It could be 5v plus 10w and so on. But then because X is in I, and I is an ordered ideal, I think Alfie mentioned that. I also mentioned it myself. So if X plus Y is in I, then X and Y both are in I. So this is the property of ordered ideals, that if sum is in I, it guarantees individual elements also in I. Okay, so now can you tell me if X is in I, which is sum of vertices, then it guarantees all these little vertices should be in I, because X is a sum of them. And if sum is in I, each of them has to be in I. So exists a U in E0 such that U is in I. Okay. Now, this is the first time I'm going to use the Serre's conjecture. So because Serre's conjecture is valid, remember that little lemma. By lemma, any U you give me is of this form, K copies of 1E. This was the lemma we proved. Okay. So now U is in I, then U is K times 1E. So K times 1E is in I. So all the vertices appear in 1E. Again, I'm using this one. If the sum are in I, each of the individuals in I. So that tells you that because all the vertices appear here, this means that for any U in E0, U is in I. And that means, of course, that I is the same as ME. So I just proved that ME does not have any ideals. ME is a simple. Okay. So ME has no non-trivial two-sided ideals. Ordered ideals. And then you saw this yesterday, that there is a one-to-one correspondence between the ordered ideals and hereditary saturated subset. So this is very nice. This was in Alfie's talks. So these hereditary and saturated subsets inside E is a one-to-one correspondence with ordered ideals. Now I just told you that ME doesn't have any ordered ideals. That means E does not have any of these special subsets. Okay. So I can have one conclusion here, because the hereditary and saturated subsets would give you graded ideals. I can say that LE has no graded two-sided ideals, i.e. LE is graded simple. And of course, E has no non-trivial hereditary and saturated subsets. Okay, so that's one thing I could get. Next, let me just show you this one also, because nice. Next, E has no sinks and no cycles without exit. Why is that? So the assumption is that projective modules are free, some algebraic assumption. Now I'm going to translate to the shape of E. Okay, I'm going to use this fact again, that any V is k copies of 1E for any V. And I get that. Let's see, how can I do this? Suppose, let's do this together. Suppose V is a sink. And eventually I want to say this is not the case. So suppose V is a sink. And write this one here. So V is k copies of 1E. And follow me here. Remember 1E, we struggle to formulate that 1E is sum of more than one element, because E had more than one vertex. So 1E has more than one vertex here. So how can you from here get that, oops, this assumption is wrong. So let's try again. V is sink. V is equal to k times V plus some other things. And from here, get a contradiction. How can I do that? The first thing you see here is equality. You have to use confluence lemma, i.e. this means that V goes to something and D goes to something. Now, how can you get a contradiction? You have to remember the definition of a sink, that there is nothing getting out of it. I cannot change V. So look, V is a sink. This is V. I cannot transform V to anything else, right? So there is no transformation here. So this stays V, 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 V. And then how can I get a contradiction here? Well, V appears here, but there are more vertices here. Any transformation you do, there are more than one appears. So there are more. If you have a vertex and you do transformation, I'm going to use this one more time later. If you do a transformation, at least one appears, but it could be more. So each time you do a transformation, you get more than one vertex. So here you have one and you have more vertex, so they cannot be the same. The same for the cycle. So if V is on a cycle, this is V on a cycle, each transformation of V gives you only one vertex. So here remains just one vertex, but here the transformation always gives you more than one vertex. So it is not possible they coincide. So good. So E has no sinks and no cycles without exit. And if you put these two together, if you put the fact that E has no hereditary and saturated subset and has no sinks and has no cycle without exit, you can see that this is exactly means that E is purely infinite simple. So I proved the first bit that the LE is purely infinite simple. And then I put as an exercise to prove that the K0 of LE is of this form. So you have to do a little bit work to show this, but it's possible. Now, the final theorem, the good one, is the one I promised, namely theorem. Question number 1 from your, if you look at your notes, means that K0 would classify purely infinite simple. That was question number 1. That if you look at, again, papers and the book, it says the most sort of interesting and open problem in this theory. So K0 would classify purely infinite simple. If this is correct, it gives us the Serre conjecture. The conjecture I put there, i.e., if this is correct, then any finite generated projective is free, therefore L is Ln. And if SC is correct, then it tells me that these two graphs have the same Leavitt path algebra. This was another one that we asked. Okay? That's why I'm saying if you say this is not correct, then this is not correct. If you say this is correct, then this is correct. So either way, you get a good thing. Okay. So let me show you a bit of, because this bit is easy. So let me show you how you. Okay. So suppose question number 1 is correct. Therefore, K0 would classify purely infinite simple. Now, suppose all finitely generated projective are free. If that happens, then we had that LE is purely infinite simple. We just proved that. And we proved that the K0, oh, this one I left it as an exercise, that this is of the form of Z and Z and 1. So we proved this is purely infinite simple. I left it as an exercise that you calculate K0 and show this bit. Okay, so I have here this, and I put here K0 of Ln minus 1, the Leavitt path algebra with n minus 1 loop, n plus 1 loop. I know that this is Z and Z. We know that. And Ln plus 1 is 1. So these two groups are the same. Question number 1 is correct. So that means that this LE is isomorphic to Ln plus 1. So this was easy. Now let me show you the other one. Namely, if the Serre conjecture is correct, then these two are isomorphic. And for this, I want you to help me because I actually didn't want to look at the computation so that you help me and see that there is a little bit, work you have to do here. So if I just put it on the blackboard, maybe you don't appreciate it. But if you struggle, you see, there is a little things need to be done. So suppose that the Serre conjecture is correct, i.e., if all finitely generated projective modules are free, then your algebra is Ln. Now, let me look at this one here. UVW. If I show that here, all finitely generated projective are free, and forget that. If you show here that for any U, you can write it as some copies of 1E. So V, you can write it as some copies of 1E, W, and here 1E is just the sum of vertices as before. If you can show me this, then that means the search conjecture is correct. Therefore, it has to be of this kind of thing. Okay, can we try this together? So you have to remember, in ME, you have only one relation, that the vertices are the sum of the adjacents. Can we show this? Let me show you the easy one and see if we can get the other ones. Let me try to show you that V is the same as some copies of this. Well, let's look at this one. V is what? V is, you have to go along all the edges and get what you end up with. One is here, V. One you get here, W. And you get here, U. And by definition, this is just 1E. So I could check it for this one. Now, how can I do it for U? This is the bit that I'm sure I'm not going to get it. It's in the paper if you want to look at it, but see if you can help me to get it. So eventually I have to get it some copies of this sum. So U is, well, let's look at this. U is U plus V. So where should I go from here now? Because you have a lot of choices. You can replace U, you can replace U, and you can replace V this way. You know, at the end, I need also a W appear somewhere here because I need to be. So maybe I just replace that. So I have U plus, instead of V, I put this one. U plus W plus V. So now what else should I do? For W, I could put W is W plus V. So I could put U plus U plus U plus V plus W plus V. Okay. And the aim is to get that many copies of all of them. So at the moment I have U, I have V, I have W, but this bit is so you see the complexity, right? So you have to work. So as I said, as I promised, I cannot get it, but have a look at the paper we have. You know, we just sat there and figured it out. And if you could get it shorter, so you see our calculation goes for 2 or 3 lines to get it eventually. If you could get it shorter, please send me an email. Let me have it. Okay, so now a couple of questions that I think it's very interesting to figure them out. I think it would be a nice research paper. Okay. Let me give you an example first that you see it's very. So these purely infinite simples. So I'm going to look at this graph. This is E. So you can easily write the adjacency matrix, and you can calculate the adjacency matrix -1. So it's a 3 by 3 matrix. So, and then use computer if you want to diagonalize that. So you can get the co-kernel, which is the, and you see that the K0, which is this thing, is Z. So already we are out of our theorem. The theorem said that if the Serre's conjecture is correct, then the K group should be torsion. So we are out of that. So our theorem guarantees that there is a projective module which is not free here in this setting. The other thing, and this might be surprising for you, is that this very special element, I mean, when I was always looking at K0, I always said, oh, this special element kind of generates the whole thing. But here it happens to be 0. Okay. So that right away tells you that not, again, all finitely generated projective are free. So either you can use the theorem I mentioned, or if this is 0, then not all finite projective modules are free, because if finite projective modules are free, that means there are n copies of these. But these are all 0. But the K0 is not 0. So then finite generated projective modules are not all free. In fact, here is a definition of stably free. See if you can imagine this one. So P is stably free if, okay, so free means that, so P is an R module. I'm writing in a general manner. P is an R module. P is free if you can write it, oh yeah, finite generated free. If you can write it as n copies of R very cleanly. Stably free means that maybe this is not the case, but you can compensate a little with Rn. So you put some more sort of bits of this Rn in here, and then you recover the complete box, so to say. Okay, so this is called stably free. And it amazed me. So give me a ring which has stably free module which is not free. Can you give me a ring which you can show me that there is a P which is of this form, but P is not a complete RK? And amazingly, this is very, very difficult. Very difficult. In fact, when you look at the book by Lamb, the second one is called, he has 2 books on ring theory. Rings and Modules is that? Lamb's book, Rings and Modules, I think. One is called the first course in non-commutative ring, and then he has another one. I'm talking about the other one. Anyhow, so if you look at that, he gives you 3 examples of such a ring. And they are amazingly very difficult. One is due to Kaplansky. I think one is due to P.M. Cohn. And one is due to, I think, Jacobson. So, and they are very, very difficult. And as you know, they call these people in 20th century, they call it the hero of algebra. These people were very famous. So anyhow, yeah, so no, try a commutative ring with this property. And this is, try a commutative ring which has a stably free, which is not free. And the Kaplansky's theorem, see if you can give Kaplansky's theorem, give you a ring, and then eventually, in order to show that whatever he produces is not free, he goes to algebraic topology. So it's not, maybe you can come up with the easier one, but what I'm trying to say is, seems to be very difficult. Now, let me just give you now with Leavitt path algebra, you know, this is one of the good things about them, that you can get very nice examples. And I give you one example of these rings, and I leave it as a project. See if you can classify them. Okay. Is this a ring that you are talking about? Is this a ring? Yeah. Okay. So that's already, if this is this example is not trivial to me. Yeah. All right. Say it again. Right, but this doesn't look trivial to me. And you are going into topology there. All right. Yeah, but I don't call that very trivial examples. But that's what I'm. Yeah. All right. Now let me. I have to inspire people. Okay. So let me give you this example. And you see, this is so easy. So let's look at this example here. So the Leavitt path algebra associated to this graph. And the claim is that this one has a stably free module which is not free. First of all, not all the projective modules are free here, because if it was, that little theorem I showed you, this has to be a purely infinite simple. I think that means everything should be connected to everything. Remember that theorem, that if all the finite general projective modules are free, then everything should be connected to everything. But here, U and V is not connected to U. So here, there exists a finitely generated projective which is not free. I didn't give you explicitly which one is this, but at least we know. Now, let me do a little calculation, and it's very easy. Let me just do this V and Z, so to be in line with my notation. So let's look at V in ME. So what is V in here? So V is V plus Z. But this one is 1E. So push this in the monoid of LE. If I want to write it in terms of projective modules, this gives me VLE, and 1E gives me LE. So VLE is free. Okay. I could not get stably free with this one. So let's try the other one. Let me try Z. Okay. And I'm going to add here 1E. And in your head, remember, stably free means you have P and you add some copies of Rn to achieve the whole complete picture. So my Rn, each of one R is 1E here, right? Place as 1E. So I just add one copy. And let's do the computation. So I get Z plus 1E is V plus Z. Okay. And I want to convince you that this is exactly 1E. Can you see that? Why is that? So 1e is v plus z. So look at this one now. V plus z is v. So I can write as v plus z, which is 1e. So I proved that z LE, this projective module, plus LE is LE. So ZLE looks like stably free. It is stably free. Now I have to convince you it's not free otherwise. But it's not free because projective modules here is either of this form or of this form or the sum of them. So this is free. I proved that this is free. If this was free, then every projective modulus becomes free. But I already said that this is not the case in this setting. So this is not free, but it's stably free. So I could produce an example. I didn't need all these difficult ones. Right. So now let me put some questions. And I think really it's a matter of sitting there and being patient to figure it out. Research questions. One, classify Leavitt path algebras such that all finitely generated projective modules are stably free. So if it was free, that would be that Serre conjecture, that it has to be Ln. I'm asking for stably free because I gave you an example that everything is stably free here, either free or stably free, right? But it's not Ln. So now, can you classify them? Two, classify LPAs, which stably free ones are free, i.e. you don't get any nice, interesting examples there. In fact, this is called Hermit ring. Any ring with this condition that is stably free is free is called Hermit or Hermiti, I don't know, Hermiti ring. In a sense of lamb, because there is also another notion of this plus IBN. So in case you're looking at that, that has been classified. So here, just this assumption here, we call it Hermit. So I think it would be interesting to classify these. How much time do I have? 5 minutes, no? So I think I'm going to stop here, and I have one more talk, and that talk is, so remember the puzzles I mentioned. One was a cat goes here, and then you get that. The other was a cat goes here, and you get a dog with some age difference. So one of them was this ME that we talked a lot. The other one was TE, and I'm going to skip the talented monoid because Alfie talked about. And the other one was if you send 3 cats and get a bunch of things. I'm going to talk about that. And that would be related to weighted Leavitt path algebra. And the sandpile model. So the last talk is going to bring these 3 together, right? To me, that's interesting because if you had 1 cat and that, you go to the Leavitt path algebra. But now you increase the number of animals, then it would be Leavitt path algebra, weighted Leavitt path algebra. And in these 2 weeks, we saw Leavitt path algebras, and we saw Gilles talk about weighted Leavitt path algebra. Oh, no, sorry. Labeled Leavitt path algebras, and Daniel talked about the the case of the ultra, which is part of it. But now I'm going to talk about weighted Leavitt path algebra, which is a different concept in the same sort of vein, but different. So yeah, tomorrow I would talk about weighted Leavitt path algebra, sand pile model, that interesting sort of domino effect it had, and which all would be towards solving this kind of puzzles. Maybe I stop here. Thank you. Say it again. Say it again. So the main there's this question, right? If they are isomorphic, that's explicitly in the book of Gene Abrams and Perry and so on. It explicitly says this is one of those main questions. This Serre conjectures, if that's true, implies that. Oh yeah, that's in this little note that we have with Rango. It's called Leavitt algebra versus Leavitt path algebra. So see if you can do it shorter then. Thank you.